I got a lot of feedback from you on the previous video where I compared Node.js with Golang. In this video, I decided to share how you can improve performance of both applications and discuss some mistakes I made in the previous benchmark. To make this test more fair, I will be using standard library for both applications to create a simple REST API. In the previous benchmark, I compared Go standard library with Express JavaScript framework. I have also got a few pull requests with improvements and I link them in the video description. To run the test, I use production-ready EKS cluster and deploy all my applications and clients that generate load to that Kubernetes cluster. This makes it more similar to what you would expect in real production environment. As always, in the first test, we'll measure P99 latency, the number of requests per second each application can handle, CPU usage relative to its limit, and the same for the memory usage. Then we'll look at the availability graph, which is a proportion of successful requests over a total number of requests for that period, and CPU throttling. For the second test, I decided to focus on Golang improvements. First, we'll discuss how Kubernetes limits affect application performance in general and compare a properly configured Golang application where the number of threads matches the actual limit set by Kubernetes against the default settings that many people use. You may know that you need to set gomax procs environment variable, and in the second test, I'll show you the real difference. My goal for these benchmarks is not only to compare performance of different applications, but also to learn new techniques to improve application performance in Kubernetes and share them with you. First, let's talk about Node.js. It is famously a single-threaded application. Technically, it creates one main thread for most operations, including I/O, and in addition, it creates 4 more threads. However, none of these are used for network I/O, such as database operations. One thread is used for DNS resolver, the second is for file system API, the third for cryptography because it's a CPU intensive, and the fourth is for compression. Most of the work is actually done on the main thread, which is perfectly fine because much of the work can be handled in the background without blocking the main thread. In some cases, this single-threaded model can even be more efficient than multi-threaded applications, and I'll explain why in a moment. The problem with a single thread is that even if you have multiple cores, a single thread will always run on one core at a time. This doesn't mean it will always run on the same core. Operating system may migrate it to another core. However, this migration doesn't mean that thread is running on multiple cores simultaneously. It's just switching from one core to another over time. The issue with the previous benchmark is that I set 2 CPU limit for both Node.js and Golang applications. We'll cover these limits in detail shortly. Node.js, due its single-threaded model, could only efficiently use a single CPU core, whereas Golang, with its much better concurrency model, could efficiently utilize all available cores and run tasks not only concurrently, but in parallel as well. Now, there are 2 main ways to improve Node.js performance on a multi-core server. The first one is to use clustering mode and deploy application on a standalone physical or virtual server. The second and better approach is to set a limit of 1 CPU and scale application horizontally in Kubernetes. That's what we're going to do in this test. But first, let's cover Kubernetes requests and limits. In this example, CPU limit of 250 is set. CPU limits and requests defined in units called millicores, which represent fractions of CPU time. For example, if you want a service to use 100% of a single CPU time, you would set the value to 1000. A value of 250 means the service is limited to only 25% of a single CPU time. Most Kubernetes clusters today use cgroups to isolate containers and manage CPU and memory allocation. Let's start with a simple example. Let's say we have a Kubernetes node with a single CPU. This could be either one physical processor or a CPU core in a multi-core processor. By default, Kubernetes and cgroups use 100 millisecond time interval to distribute CPU time among all applications running on the server. You can think of one CPU defined in Kubernetes limit as equal to 1000 millicores, which translates to 100 milliseconds of CPU time. For example, if you set a limit of 250, it would correspond to 25 milliseconds of CPU time within that 100 milliseconds interval. If the application exceeds the time defined in Kubernetes limit within that 100 millisecond interval, Kubernetes starts to throttle it, which you can see in this graph. The key to better understand is to think of the 100 milliseconds as enforceable interval that Kubernetes uses via cgroups to apply those limits. In cgroup v1, this was managed using quota and period files. Cgroup v2 removed this and replaced them with a single CPU.max file, which contains both quota and period. For example, let's say we have application with 250 limit. On the node, the cgroup configuration would look something like this. The first value represents the quota, which is 25,000 microseconds, translating to 25 milliseconds and 250 millicores. The second value is enforceable time interval, which is 100,000 microseconds or 100 milliseconds, which is the default setting. This 100 milliseconds cycle repeats continuously as long as there are containers running on that node. Since we have one CPU, which equals 1000 millicores, this translates to 100 milliseconds interval. So with a single CPU, we have 100 milliseconds of CPU time that can be shared among all the services running on the node, proportionally distributed according to their assigned CPU limits. If there was only one service running on the node, you can assign the full 100 milliseconds of time to that service for each cycle by setting CPU limit to 1000. If two services were running, you might want them to share CPU equally. In that case, you would assign each service 500 millicores, giving each 50 milliseconds of time within every 100 milliseconds cycle. Similarly, if four services were running, you can assign each 250 millicores, giving each 25 milliseconds of CPU time within the same 100 milliseconds cycle. Now, CPU time doesn't have to be distributed equally. For example, you could assign one service 500 millicores, which is 50 milliseconds. A second service 100 millicores, which is 10 milliseconds, and the remaining two services 200 millicores each, which is 20 milliseconds each, for a total of 1000 millicores or 100 milliseconds across all services. When a node has two CPU cores, it now has 2000 millicores or 200 milliseconds of time per cycle that can be allocated to the different services running on it. For example, you can set a limit for one service to 1500 millicores. This service would then use a full 100 milliseconds from one CPU and 50 milliseconds from the other. Now, if there is another service with 500 millicores limit, it would take the remaining 50 milliseconds from the second CPU. As you can see, the more CPU cores you have, the more CPU time is available, allowing you to schedule more services on that node. Up to this point, we have assumed that each service has a single thread running for the entire interval. However, in reality, this isn't the case. There is no CPU affinity, and OS threads are typically subject to a 10 milliseconds time slice managed by the operating system, meaning the thread will migrate between cores. Now, let's say you have 4 threads running on a 4-core node, like in my previous benchmark with Golang application. Golang will create as many threads as there are cores. In my previous video, I used extra large instance, which has 4 CPUs. If I set service limit to 250 and I have 4 threads running in parallel on all available cores, that limit will be reached 4 times faster. This will result in extra context switching, reducing the amount of work done over time. In the end, this is the key point. A limit of 1000 millicores or 100 milliseconds or lower means the service will use only one CPU's worth of time per cycle. For services written in Go, understanding this is crucial as Go programs tend to be CPU bound. With CPU bound programs, you never want more OS threads than you have CPU cores. And that's why we need to set GoMax procs to match the number of cores available to our program. You can read more about Golang optimizations in this article. To run these tests, I use production-ready EKS cluster in AWS, and I use Graviton instances to run my clients that generate load, simply because they're cheaper. Alright, let's go ahead and deploy both applications to Kubernetes. Since we're deploying multiple pods for each application, I'll use average CPU and memory usage for all replicas, rather than tracking every single pod individually in this video. For the first test, I set Go max procs to match the limit defined in Kubernetes. You can hardcode it to 1 in this instance or dynamically pull that value as a reference. Alright, let me start the test and deploy Kubernetes jobs to begin generating load. At the start, you can see that P99 latency for Node.js is slightly higher, and it also uses a bit more CPU. I have clients that slowly increase the number of virtual users until both applications start to fail. You can also notice that Node.js uses more memory or at least exhibits different behavior. Up until 16,000 requests per second, Golang's request latency is lower, but it gradually starts to converge at this point, and eventually Golang's latency becomes higher for a while. By the time we reach 34,000 requests per second, you can start to see that Node.js is being throttled by Kubernetes, and occasionally there are noticeable spikes in latency. At this point, Node.js begins to drop many requests and becomes unstable. At around 46,000 requests per second, Golang also starts getting throttled, and you can see its latency increasing as well. At around 52,000 requests per second, Node.js is heavily throttled and can no longer handle any additional requests. However, its latency is still quite close to Golang's, so it remains within acceptable limits. At around 70,000 requests per second, Golang starts to fail as well. In this test, we have 2 pods with 1 CPU limit each, so each instance can handle roughly 35,000 requests per second. Alright, let's take a look at the graphs for the entire test duration. First, we have requests per second. You can see that in this video, Node.js processes many more requests than in the previous benchmark, thanks to setting the CPU limit to 1 and scaling horizontally rather than vertically, as in the previous test. At around 36,000 requests per second, Node.js starts to degrade, but it can still process some additional requests. Next, we have P99 client latency. Lower is better. Node.js latency is higher, but it's not as dramatic as in the previous benchmark. I would say it stayed within acceptable limits throughout the test. It only reached 20 milliseconds. Now, let's take a look at the latency before both applications started to degrade. I would even say that Node.js is a little more stable than Golang. Yes, the latency is higher, but it has fewer spikes until it reaches the point where it begins to significantly slow down. Next, we have CPU usage. The more CPU application uses, the sooner Kubernetes will throttle it. And when that happens, latency goes up. So it's always important to monitor how much CPU your application is using. Next, we have memory usage. If we continue to increase the load, Golang will start caching more and more requests, eventually reaching 100% memory usage and getting killed by Kubernetes with out-of-memory error. Next, availability. I set a timeout of 1 second for each client, and that limit was never reached by any of the clients. So that's why we have 100% availability in both cases. Finally, CPU throttling. Since we set the number of threads that Golang can use to 1, there was less thread migration and wasted CPU, improving performance and reducing throttling. That's all for the first test. Node.js is still very competitive, but it's a little slower and requires more attention to deployment due to its single-threaded nature. So from the start, I would suggest thinking about how you can horizontally scale your Node.js application and perhaps have autoscaling in place. Alright, let's go ahead and run the test between a properly configured Golang application and a typical default deployment where you ignore underlying hardware and do not limit the number of Golang threads to match the number of CPUs available. At the start, you can see that P99 latency is lower for the properly configured Golang and it uses less CPU time. The default Golang setup refers to a deployment without setting Go max procs to match the number of CPUs allocated to the application. Both applications have one CPU limit, but the default setup tries to create as many threads as there are cores, in this case 2. You'll see a noticeable difference between the properly deployed Golang application in Kubernetes and the default approach, where the number of threads is not adjusted for Golang. It's quite a big difference. In this test, we also deploy 20 pods, gradually increasing the number of virtual clients from 1 to approximately 100 for each pod. So by the end, we have around 2000 virtual clients generating the load in Kubernetes. When we reach 30,000 requests per second, you can notice that latency for both applications increases, reaching 1 millisecond, while CPU usage approaches 50 to 60%. At this point, you can set up horizontal pod autoscaler to increase the number of replicas when CPU usage reaches around 50% or maybe slightly higher. You need to load test your application and find out at what point it starts to degrade, as different applications have different bottlenecks. Some are CPU bound, memory bound, or network bound, etc. At around 36,000 requests per second, we start to notice that Kubernetes begins throttling our default Golang application. At around 53,000 requests per second, Kubernetes starts to heavily throttle default Golang setup, which represents the maximum number of requests default Golang application can handle. Let's keep going until the properly configured Golang app starts to fail as well. At around 70,000 requests per second, you can notice slight throttling of Golang, and this represents the maximum number of requests it can handle with this configuration. Let me go ahead and open each graph for the entire test duration. First, we have requests per second. The default Golang deployment was able to handle only around 53,000 requests per second, while the properly configured version handled around 70,000 requests per second. So there is a significant difference. Next, we have latency. You can see huge spikes in latency due to thread migrations and throttling. Every time Kubernetes throttles application, latency and overall performance decrease. Next, CPU usage. Once again, the default setup uses more CPU because it has more threads, and due to thread migrations, it wasted more CPU. Next, memory usage. Memory usage is slightly higher because the default setup is slower and caches more requests. Also, there are no changes in availability. The most important metric for this test is throttling. You can see that the default Golang application is throttled much more than the properly configured Golang with a single thread. This demonstrates that by understanding how Kubernetes limits work, you can significantly improve performance of your Golang application. This specific environment variable is only applicable to Golang, and when I move on to other languages, I will also highlight how to efficiently deploy them in Kubernetes. I have other benchmarks that you might find interesting. Thank you for watching, and I'll see you in the next video.